Welcome to all of you. To this point, we have learned how to take Laplace transform of a given function, and we have derived a list of formulas. So we were looking at the function of s, and if we go backwards to the function of time, and that's very important. So in this lecture, we look at the problem of finding inverse Laplace transform of a given function. So in the last few lectures, we saw the definition and some properties of the Laplace transform, and some related problems have been discussed. So we will start with the basic definition of the inverse Laplace transform, some properties and some examples in which I will discuss the procedure of calculating inverse Laplace transform of a given function. So let us come to the definition of the inverse Laplace transform. So given a function fs, the inverse transform of f, which we denoted by L inverse of this fs, is that function small f whose Laplace transform is capital F. So more specifically, if the Laplace transform of a function ft is equal to fs, or if I just invert it here, so the inverse Laplace transform of fs is giving us f of t, so that's a function of time. So for example, suppose if I want to determine the inverse Laplace transform of a function 1 over s square plus 9, so that means I want to bring it back to the time domain, a function of t, when we are finding the inverse Laplace transform of a given function. So if you look over here, we have already derived the formulas for L of the Laplace transform of a function sine at, which we have already derived to the a over s square plus a square. Or if you just write it in the form of inverse Laplace transform, so inverse Laplace transform of 1 over s square plus a square is nothing but your 1 over a sine at. So if you use this formula to determine the inverse Laplace transform of function 1 over s square plus 9, what I'm going to do here is that I'm going to multiply and multiply this 3 in the numerator and denominator. So I can write it as the inverse Laplace transform of 1 over 3 times 3 over s square plus 9. Now 1 over 3 I can take it outside here. So the inverse Laplace transform of 3 over s square plus 9. So if we use that formula, so that can be written as 1 over 3 sine 3t here. So that's the inverse Laplace transform of this function 1 over s square plus 9. Okay, so I'm going to look at some of the properties of the inverse Laplace transform. So the first property we are going to discuss, which is something called the linearity of the inverse Laplace transform. So this is a theorem. So basically, if we have the inverse Laplace transform of a function fs is equal to ft, and if the inverse Laplace transform of another function gs is equal to small gt, so then the inverse Laplace transform of alpha times capital Fs plus beta times of capital Gs is equal to, I can take this alpha outside, so alpha times L inverse, that means the inverse Laplace transform of Fs plus beta times of inverse Laplace transform of this Gs. So that means basically that inverse Laplace transform is a linear operator, and where this alpha and beta are the constants. The another property which is a very useful property, and that is something called the shifting property for the inverse Laplace transform. So basically, if we know that the inverse Laplace transform of capital Fs is equal to ft, so then what it says here, that the inverse Laplace transform of f of s minus a is equal to e raised to the power at times ft here. So this is the proof given here. So we will start with this by finding the Laplace transform of this function e raised to the power at times ft. So by definition of Laplace transform, it can be written as 0 to infinity, the integration from 0 to infinity, e raised to the power minus st, and inside this bracket we have e raised to the power at times ft. We are integrating it with respect to t here. So we are just using the definition of the Laplace transform here. So I can again rewrite this expression something in this way, that from 0 to infinity e raised to the power minus I'm taking this common, and s minus a times ft dt, and which is nothing but the function capital F of s minus a. So I can rewrite this as, if I take the inverse Laplace transform of f of s minus a, and which is going to be equal to e raised to the power at ft. So this is something known as the shifting property for the inverse Laplace transform, and we are going to use this shifting property to solve some kind of problems. So these are some standard formulas for the inverse Laplace transform of a given functions. So we have already derived the things like the Laplace transform of 1 is equal to 1 over s. So similarly we are just writing it in the backward to the of the function L inverse of 1 over s, that is equal to 1 here. Okay, so students are advised to memorize these results so that they can use it quickly whenever it is needed here. So these are some standard formulas which I have just mentioned it here. So for example, I'm going to discuss few of the examples of the Laplace transform. So we want to find out the inverse Laplace transform of these two problems here. That the first one is s square minus 3s plus 4 over s cube, and the second one is that s plus 2 over s square minus 4s plus 13. So if you see these two functions here, these two functions are not in any of the standard forms. So we cannot directly use any of the formulas for the Laplace transform which we have just derived it in our last lectures. So what we are going to do is that we are going to convert these functions in the standard forms here. So first of all, I am just going to rewrite this expression that L inverse of s square minus 3s plus 4 over s cube. So I am going to individually divide it by this s cube in all the terms here. So this can be rewritten as L inverse of 1 over s minus 3 over s square plus 4 over s cube. And again, if we use the linearity property, so again I can write it as L inverse of 1 over s minus 3 times of L inverse of 1 over s square, because 3 is constant. So by linearity property we can take this 3 outside, plus 4 times of L inverse 1 over s cube. So again we can take this 4 outside because of the linearity property. So again, if you look over here to the formulas of Laplace transform of this Tn is t raised to the power n is equal to factorial n over s raised to the power n plus 1. So again I can, if I write it in the form of this inverse Laplace transform, so the inverse Laplace transform of 1 over s raised to the power n plus 1 can be written as t raised to the power n over factorial n. So if you use this formula, I can write this L inverse of 1 over s equal to 1 here, L inverse of 1 over s square equal to t here, so that's going to be your 1 minus 3t, and the L inverse of 1 over s cube, that's going to be your t square over factorial 2. So finally what we got it here, that 1 minus 3t plus 2t square. So this is the inverse Laplace transform of this first problem here. Let us look at the second problem here of finding the inverse Laplace transform. So again, let me mention it here, this is also not in any of the standard form here, so we cannot directly use for the inverse Laplace transform here. So what we are going to again do it here, we are going to convert it in the standard form here. So first we are going to make this denominator as whole square. So I can always write it as L inverse of s plus 2 over s minus 2 whole square plus 9, and again in the numerator I am going to add and subtract this 2 here. So this will become L inverse of s minus 2, and if I add 2, so that will become here 4 plus 4 and divided by this s minus 2 whole square plus 9. So again, if you use the linearity property, I can write it as L inverse of s minus 2 over s minus 2 whole square plus 9 plus 4 times of L inverse of 1 over s minus 2 whole square plus 9. Again, I am going to use the shifting property here. So if you use the shifting property, I can write it as e raised to the power 2t L inverse of s over s square plus 9 plus 4 times of e raised to the power 2t L inverse of 1 over s square plus 9. So this I am writing it using the shifting property. And then again we already know here that what's the formula for this L inverse of S over S square plus 3 square here. So that's nothing but your cos 3t, and the formula for L inverse of 1 over S square plus 9 is nothing but your sin 3t. So the final expression for the inverse Laplace transform of the second problem we have obtained is that e raised to the power 2t times cos 3t plus 4 over 3 times e raised to the power 2t sin 3t here. So this is the inverse Laplace transform of this second problem. We are going to look one more problem where we want to find out the inverse Laplace transform of 4s plus 5 over s minus 1 whole square s plus 2. So again, if you see this function here, this function is not in the standard form, so we cannot directly use any of the formula for the inverse Laplace transform. So what we are going to do is that we are going to, for this function, we are going to resolve it into the partial fractions here. So first of all, we will write this function 4s plus 5 over s minus 1 whole square times s plus 2 equal to a over s minus 1 plus b over s minus 1 whole square plus c over s plus 2. So finally in this equation I am going to multiply throughout by s minus 1 whole square times s plus 2. So this will take this equation that 4s plus 5 equal to a times of s minus 1 s plus 2 plus b times s plus 2 plus c times of s minus 1 whole square. If I just multiply this s minus 1 s plus 2 and if we open the square s minus 1 whole square, so after opening these expressions and if we compare the coefficients of s square, s and the constant term, we will obtain these three equations: a plus c equal to 0 and a plus b minus 2c equal to 4 and minus 2a plus 2b plus c equal to 5. So this is a system of linear equations, and if we solve these simultaneous equations, we'll obtain the value of these unknowns, that a is equal to 1 over 3, b is equal to 3 and c is equal to minus 1 over 3. So finally we are going to use these values of a, b and c in this expression. So the inverse Laplace transform of this 4s plus 5 over s minus 1 whole square times s plus 2 will be equal to this 1 over 3. So we are using the linearity property, so we are taking this 1 over 3 outside, and the inverse Laplace transform of 1 over s minus 1 plus 3 times the inverse Laplace transform of 1 over s minus 1 whole square minus 1 over 3 the inverse Laplace transform of s plus 2, 1 over s plus 2. So we already know the formula of the inverse Laplace transform of 1 over s minus a, that is equal to e raised to the power at. So if we use that here, so L inverse of 1 over s minus 1 will become e raised to the power t, because if we compare it here with the formula, a is equal to 1 here. And if we use the shifting property, so L inverse of 1 over s minus a whole square can be written as e raised to the power at L inverse of 1 over s square. So that can be written as e raised to the power at times t. So the inverse Laplace transform of 1 over s minus 1 whole square will become 3 times t times e raised to the power t, and the inverse Laplace transform of this last term, that is L inverse of 1 over s plus 2, will become e raised to the power minus 2t. So the inverse, finally we have obtained the inverse Laplace transform of this function, that is equal to 1 over 3 times e raised to the power t plus 3 times t times e raised to the power t minus 1 over 3 times e raised to the power minus 2t. So in the next lecture we will discuss more methods of finding the inverse Laplace transforms. Thank you very much.